Hello, everyone. Thank you for taking the time to be here. My name is Skinjal,
And my name is Anushri.
and we're so excited to present our work to you.
Yes, really excited to share with you our work regarding artificial intelligence and SAS Via in order to enhance crime hotspot prediction.
So for some quick introductions, my name is Skinjal Chaudhary. I'm a junior studying computer science at the University of Illinois at Urbana-Champaign with a focus on artificial intelligence. I really love exploring the newest technologies and like the newest breakthroughs in AI and ML and finding innovative applications to bring them for real-world problems.
And my name is Anushri. I am graduating from U of I next week with a major in statistics and minors in computer science and legal studies. I kind of bring all of the theoretical knowledge behind statistics and machine learning concepts, as well as experience working with big data. And at the end of the day, I really just enjoy sharing and helping others understand complex data problems. Right, so when we first started this project, our goal wasn't just to make predictions. It was to create something that is actually useful and functional. Something that could actually help cities become safer. But of course, in order to do that, we first had to thoroughly understand the problem that we are solving. What we found is that urban crime isn't scattered randomly across a city. It's very concentrated. In fact, as of 2021, the National Institute of Justice reported that 50% of violent crimes occur in less than 5% of city blocks. This means that if we can identify those concentrated, high-risk areas in advance, we can make a huge impact even with limited resources, and ultimately, hopefully transform modern policing for the better. But here's the challenge. Traditional policing methods rely on historical calls for service, meaning they're reactive, not predictive. That can lead to under-policing in some areas and over-policing in other areas. We, of course, wanted to flip that script, to use the data not just to look backwards, but also to look ahead, and to do it in a way that is fair, explainable, and actually useful to our public safety teams. And this is where our AI-based crime hotspot prediction comes in.
But just identifying these crime hotspots isn't enough. Without fairness safeguards, AI tools can actually make the problem worse by reinforcing bias and making unreliable predictions. Now, this concept, hotspot prediction, isn't new. We've actually found many models that attempt to do this, but a lot of them don't account for the spatial and temporal depth that's needed to make accurate forecasts, especially in urban and city environments. That's why we've built our model with both predictive reliability and fairness at the core, because in public safety, getting it wrong has major consequences. So here's how we made it work. We used over 20 years of Chicago crime data to predict not just where crimes might happen, but when. That time dimension is crucial for anticipating patterns before they escalate. With SAS Via, we processed and analyzed these large data sets at scale, enabling fast and accurate predictions. And at the heart of it all is a really cool spatiotemporal graph convolutional network, which is a deep learning model that captures how crime moves through space and time.
So to begin, let's first just get to know our data. This dataset in particular stood out to us for its very specific temporal and geographic features, everything from the exact time of day down to latitude values, longitude, and X and Y coordinates. We also found that there were very convenient categories and descriptions of the type of crime occurring, again allowing for easier crime prediction. We also found that this data was in an event-based structure, meaning every single row represents a specific crime that occurred. This allowed for easy anomaly detection. Ultimately, we ended up cleaning about 86,000 rows of data due to missing latitude and longitude values. We, of course, checked the distributions of these attributes of those rows to ensure that the distribution lined up with the overall distribution of the data. Thus, we were able to safely remove these rows, and we still ended up with about 7.7 million non-null rows of data, still a very big data set coming in at over 10 gigabytes. Of course, this is also a constraint, just working with big data in general, and the event-based structure also definitely added some extra pre-processing steps for us to implement, as well as a lot of very heavy aggregation, as you will see on the next slide. So for attributes that we considered, again, focusing in on those spatial and time-based features, latitude, longitude, block, location description, as well as the date of the crime occurring. We also wanted to include those categories and descriptors of crime, thus including primary type and description. We also created some attributes. So we created bins for the latitude and longitude values. And these values were rounded in order to create these bins, resulting in a square grid that encompasses Chicago. And within this grid, each square is approximately a square kilometer. We created two different types of targets. The first type is a binary variable called crime-prone 0. This essentially just measures whether or not at least one crime occurred daily over the course of the week. This binary variable we really just created for the purpose of using a logistic regression model. We also created crime-prone, which is similar, but instead of just binary, it offers us 3 different levels, again measuring frequency of crime. For example, 0 represents the fact that less than 5 crimes occurred during that week. So with all of this, where does SAS Viya come in? SAS Viya's key utilizations in our project are condensed into 4 main categories that you can see here. First, we used the Cloud Analytics Server, or CASLib, to store and access our massive, over 10 gigabyte data set. Having this persistent global access made a huge difference, especially when we were collaborating across different stages of the project or even accessing the project from different devices. Since we are students using Viya for Learners, there are, of course, limitations on the features that we can access, such as a limit on the size of the data that we can upload. We actually found Jupyter Hub to be an amazing workaround for this. It allowed us to connect to the CAS server, upload larger data files, and even push the script to our GitHub repository. This was essential for the early stages of our project, where we were able to import a large data set, of course, but also work in a coding environment that we were already familiar with. Next, we used the Flow application in feature engineering for our different pipelines, and the Flow application was really crucial in organizing the different feature engineering pipelines for our different models. Next, we used the Build Model and Model Manager tool. This was honestly lightning fast in creating and tuning multiple different machine learning pipelines. It also helped us streamline the entire process, everything from training to validation to model deployment. So finally, let's dive into our first use of the Flow application. Over here, you can see that the bulk of our data pre-processing was done in Flow. Over here, in the specific example, we were able to connect different nodes that integrate SAS, Python, and SQL into the same pipeline. In this specific pipeline that you see, we started off with just the raw crime data, and you can see that we, along the way, aggregated this data, generated statistics, and also created subsets along the way so that we can kind of peek into our data and make sure that everything is all right after each major pre-processing step. So we had 3 different flows, just like this one example, to prepare for our model pipelines. And while we were in this exploratory data analysis phase, we also decided to try out Viya's interactive dashboard. Over here, you can see we dabbled in the dashboard a little bit to really just understand the nature of the data. you can see very clearly that over the decades of data, there are visible patterns and visible trends. Again, just kind of reassuring us that there is incentive to continue with this analysis. There are trends that we can latch onto and dig further into. So getting into our actual model building, we used the Build Models application, starting off with the dataset that includes just the binary response. With this, we created the logistic regression model, a support vector machine model, and gradient boosting. And you can see, looking at all the nodes that are connected, visually, this is just so nice to look at, compared to what we would do previously with just chunks and paragraphs of Python and R all stacked on top of each other. This is very nice to look at, very easy to tune the parameters by just clicking on the node for each model. And the very last node is actually for model comparison, which was also really convenient. So with this specific pipeline, we were answering the question, given the previous week's crime data, longitude and latitude bin, and current week of the year, for this week, will this area be crime prone or not? Next, we did something similar using the dataset with the ordinal response that has the 3 different levels. Over here, of course, since it's not binary, we removed the logistic regression and kept the SVM and gradient boosting. And again, keeping the model comparison node for SAS Viya to select the best model at the end. With this one, we're answering a similar question. Given the previous week's crime data, the longitude and latitude bin, current week of the year, for this week, how crime prone will this area be? Instead of just, will it be crime prone or not? And you can see our results in the next slide over here. So again, SAS Viya just kind of automatically outputted this for us with the model comparison node. And you can see, starting with the binary response data set, SAS Viya thought that the gradient boosting model would be best. And you can see that the gradient boosting model had an accuracy of about 97.14%. This is actually interesting because the logistic regression model did have a higher accuracy of about 97.45%. However, if you dig deeper and if you keep looking at the numbers, you can actually see that the gradient boosting model has a higher area under the ROC curve, which gives us some insight as to, okay, maybe this is why SAS Viya chose to go with the gradient boosting model. Again, very nice that it just does this for us. Moving on to the ordinal response dataset, we see that it chose SVM, and this one achieved an accuracy of about 95%, definitely lower than the binary response dataset. However, when you think about it, it's kind of like a trade-off, because the binary response dataset, yes, it has a higher accuracy, but with our ordinal response, it does give us a little bit more insight as to the level of frequencies of crime occurring. And you can see the ROC curves that I mentioned over here as well. It is a little hard to see because they're all so close, but with the ordinal dataset, you can see pretty clearly that one has more area under the curve as opposed to the other. So throughout this whole process, we picked up on several key advantages of using SAS Viya. Again, we come from a background of just using Python and R for everything, so this is very different. First of all, again, being able to import such a large data set and work with it so quickly, especially during model building. Number 2, we were able to clean and manipulate our data so well using Flow. 3, the train and validation split, again, something that we would typically think so much about and probably have a couple of lines of code to do it. It was literally just built into the build models. So something that we didn't even have to think about with SAS Viya. Number 4, again, the parameter tuning with the models was very convenient. Number 5, the model comparisons that you just saw. And 6, we saw that after our models were all built, there were many bias assessment features available for us to use and gauge the bias of our models.
All right, and I'll take it from here. So, after working with SAS Viya's classical models, a few takeaways become clear. Crime isn't just tied to one place or time. it changes based on patterns. So from all of our explorations with SASVAIA, we saw that there are trends tied to hour, day, and season, but also that nearby locations often mirrored each other. And these patterns weren't static, they evolved. And classical ML models just aren't built to capture that kind of movement. And so that's why this became a deep learning problem. Because to truly predict and adapt to these shifting dynamics, we need a model that can understand both space and time together. Now, I know we're at an AI conference, so I'm sure most of us are familiar with deep learning and neural networks, but for anyone that could use a quick refresher, here's a simple breakdown of how it works. At a high level, a neural network is just a system that learns patterns from raw data. What makes it powerful, though, is its ability to capture complex, nonlinear relationships that traditional models might miss. So it'll start with a forward pass. Our data will move through the layers of the network from input through hidden layers to the output, each one transforming the inputs to get closer to a prediction. Now, based off of that initial prediction, the model will calculate a loss compared to the actual value, which will just be a measure of how far off our prediction was. Then we'll move into backpropagation, where the network will adjust its internal weights within the hidden layers to reduce that error, to reduce that loss, and then therefore increase the accuracy of our prediction. And this process will repeat over and over again until our predictions improve and our loss is minimized. And this foundational structure is what powers many modern AI systems, and it's the backbone of the more specialized deep learning architecture that we'll get into soon for this crime hotspot prediction. So now that we understand how deep learning works in general, let's talk about how it is applied to crime prediction. So on the temporal side, we wanted the model to learn how past events can influence future risk, so capture the short-term spikes and the longer seasonal trends. Models like recurrent neural networks or LSTMs are typically used for this kind of sequential data because they can remember and process patterns over time. And on the spatial side, we knew that a simple grid-based method wouldn't cut it because cities aren't perfect grids. So instead of treating every location as independent, we needed something like convolutional layers to capture the influence of nearby areas, but we took it one step further with graph convolution. And this lets us model irregular and real-world type spatial connections. And that sort of intuition led us to the spatiotemporal graph convolutional network, which, it's a mouthful. I'll just call it the STGCN from now. It's designed to learn from both of these structures at once, helping us make smarter, more context-aware crime prediction. For training purposes, we first had to structure our raw crime data in a way that this model can actually understand and make sense of, and that started out with building 4 features. So similarly with how we did in the SASVAIA, we created spatial grids by just binning the latitude and the longitude into cells, each with a unique node ID. For temporal, again, we just grouped the crime into intervals so that we can capture when events were happening throughout the day. After that, we moved to aggregating the data. So for every time step and node ID pair, we create a feature set. One of them is crime occurred. So 1 if the crime happened, 0 if it didn't. And then crime count, which is just the total number of crimes. And finally, we create a temporal output for our STGCN by combining all of this into a 3D tensor with the shape T, N, and F, where T is the time, N is the number of nodes, and F is that feature set. So here's a quick look at our full pipeline. We'll start with the raw crime data, just latitude, longitude, and the timestamps, and pre-process it into grid cells with labels. Then we'll build our 3D tensor for the temporal time information, and then we represent our spatial information with a spatial adjacency matrix. So both of these are our inputs to the STGCN model. We'll get into the architecture of the model next, but basically what it's doing is it's stacking spatial and temporal layers. It's adding attention mechanisms so that the model can focus on what matters, and it outputs a crime risk map. So getting into the architecture, we start with that 3D tensor that we just talked about, and plus the normalized adjacency matrix that tells the model how spatial nodes are connected. In block 1, we'll apply a temporal convolution, and through that we'll learn time-based patterns, followed by a graph convolution to share information across the spatial regions that are connected. And then another temporal process combines all of those signals, and a residual connection keeps all of that information flowing cleanly. Then we stack block 2, which repeats that same structure to refine the temporal and spatial patterns even further, which improves the depth and stability of the model. After that, we introduce the attention mechanisms, so one for time and one for space. And this allows the model to focus on the most important nodes, so like the most important regions of space and periods of time for this prediction. And finally, we'll send everything through a fully connected output layer that will give us a risk score for each grid at each timestamp. And we'll use these outputs to actually overlay on a map of Chicago to give us a crime risk map. So after tons of debugging, tuning, and rerunning, the model ended up performing very well. We hit a 97.09% accuracy. It converged fast, and the loss stabilized eventually under 10 epochs. It was able to learn spatiotemporal crime dynamics from our data, and in terms of scale, we processed millions of data points. Might I remind you, over 20 years worth of data across 744 locations and over 195,000 hours, all while keeping data fast at 300 samples per second. And so this translates into millions of predictions across real-world city grids, powering real-time crime risk monitoring. Now, besides the metrics, let's go into what this means, what it would look like. So we have a couple of visualizations. This heat map shows how the model predicts crime intensity across city grid cells, where the brighter regions represent area with higher predicted crime on average. So you can see that we have some high averages in that yellow region right there. Here's another visual. Here we're showing how the model captures temporal patterns over time at a specific location. So each spike or dip reflects changes in crime activity. This proves that the STGCN isn't just identifying static hotspots. It's learning dynamic behavior like surges, declines, and consistent trends, helping flag risk as it evolves. And finally, this visual really brings everything together. By overlaying our predictions on a real Chicago map, we can see these high-risk zones light up. This isn't just deep learning at the end of the day. It's not just data science. It's not just artificial intelligence. We're seeing these outputs that can truly help drive public safety and urban planning or even community outreach. All right, so we've learned a lot, so let's just take a moment to reflect. Overall, this solution shows how we can turn data into real-time insights that actually help people. By identifying risks and visualizing them clearly, we can help bridge that gap between artificial intelligence and public safety.
Sorry. Looking ahead, we hope to expand the data set with newer reports, add more contextual signals such as weather or events that are happening in the world, and even hopefully we can move towards multi-step forecasting to get even more proactive.
And thank you so much for your time. It's really rewarding to be here and share our work. We'd love to stay connected and keep the conversations going around AI or data science or even work for the public sector.
Yeah, enjoy the rest of the conference, and definitely feel free to reach out and stop by if you guys want to chat with us. And yeah, we'll take any questions if there are any. Yeah.
I don't know a lot about AI, but I was just curious if you do use this forecasting and a lot of those frequent hotspots are busted, is this like the 20 years of data you have? Is that still going to be relevant if criminals like decide to use different places? Like, how do you think that would work after using this data?
You want to do it, or can we talk? Okay. Yeah, I mean, see, the data set we had, it was off of Kaggle, so it only showed us reports up until 2023. But, with newer reports, again, using those pipelines that we had built within SAS Viya, we can continue literally just adding on to the data set. Again, like we said, with newer reports for more recent crimes happening. And yeah, I don't know if that answers your question, but.
And then I would just want to add, for something, I guess for like any sort of like AI usage to be continued on in future work, we would want that data set to be as relevant as possible. So I guess part of that future work would be collecting relevant data still and continuing that process and making sure that it is robust and accurate so that we can keep our models up to date, so that we can account for changes that are made in these urban environments, like crime changing or patterns changing.
Yeah,
But yeah, good question.
Kind of like a more, like maybe specific example, if you want, would be, I actually completely forgot to mention this, but when we were preparing our data and pre-processing everything, one of the attributes that we created was called lag data. So essentially, it isn't any new data, it's data from within our data set, but it's telling us the frequency of crime that happened last week, the week before, and even 3 weeks ago. So for example, data like that, it's as recent as the week before, So again, we're still, I guess like with new data, like we would still have other attributes that can tell us, something like lag data that can tell us, okay, like what happened the week before and does that influence what is going to happen today or this week?
Yeah. All right. Thank you.
Thank you.